Good evening, my name is Gonzo, and what we're going to look at today is a slightly more statistical method of predicting football games. We're not actually going to get all the way to predicting football games, but we are going to look at this distribution here, which is the Poisson distribution. There are lots and lots of different kinds of probability distributions. The first one you get introduced to when you do high school statistics is the normal distribution, which is a Gaussian curve. And broadly what we're saying with all of these is that they are a way of us understanding how the probability of an event is distributed. And we're interested in the Poisson distribution because, if you go ahead and read the Wikipedia article, what a Poisson distribution does is it gives you the probability of a given number of events occurring in a fixed interval of time. This is really important for predicting things like football goals. The reason it's really important is kind of self-evident. We want to know how many events, a team scoring a goal or the number of total goals that get scored, happen in a fixed time. Okay, we're going to hand wave a little bit and assume that every football game is 90 minutes long. It's a fixed quantity of time. They play actually for 90 minutes, give or take some tiny error bars. But you don't have to take my word for it, okay? So this is the formula for the Poisson distribution. So the probability of k events in a interval is given by this formula when you expect lambda events. So what this basically means is that if I have an expectation of a number of goals, so if I'm going into a game and I say, I think the most likely number of goals that will get scored is 3, then what actually is the probability of there being like 4 or 5 or 6 or 2 or 0? And what the Poisson distribution does is it describes that to you. If you decode this formula and you write that out, so if I expect 3 and I want to know what's the probability of there being 4, then we replace lambda with 3 and k with 4, and then you solve that equation. And you don't have to take my word for it, okay? That's what this graph here is. It is a matching of the Poisson distribution over the total number of goals scored on average in an English league game. So in order to do that, what I've done is I've taken all of the games that we've looked for the data of in the previous 3 videos, so pulled in all of the English league data, and then I've used the mean number of goals across all of that data as the central point of the Poisson distribution and said, well, actually, look, if you're going to come to any arbitrary game in England, what you should do is you should expect that they'll probably score 2.59 goals. Now, obviously you can't score 2.59 goals, but that's what my prediction is. And from a betting perspective, if my prediction is, well, they're going to score 2.59, what I'm really interested in is, like, what is the probability of them scoring 3 or 2 or 1? And then I can kind of set a line and understand the odds. If we take that mean number as our expectation and match a Poisson distribution over the total number of goals scored, it's pretty good. There are some obvious deviations, okay? If you look at the number for 3, then the actual observed number for 3 is higher than what the Poisson distribution expects, and the observed number for 4 goals is lower than what the Poisson distribution expects. And towards the end of the video, we'll discuss why that might be and what we can kind of do to combat that and, using this model going forwards. But for now, let's dive into it and construct it so that you understand where this comes from and how you can use it. By the way, if you're looking at this and you're like, Gonzo, that's a lot of code, I've never seen all this before. All of this is available on my GitHub account, okay? It's in a different repository than the one that we've been playing with, where we've been building things up slowly over time so that everybody understands what we're doing. This is just where I've been playing about. Some of this has been exposed on TikTok. I've got an account on TikTok which is reasonably successful. You should go there. That's where I kind of started all this garbage. Much of this code is explained kind of there, but we're building it up together. So the first thing that we're going to need to do is we're going to need to get into our terminal, because we need an extra module in order to be able to do these things nice. We're going to need the module SciPy, which is just a statistical handling library in Python. So we're going to do add SciPy into where we are, and then we're going to just go ahead and start JupyterLab again. And that will give us a place to play. Here we are, and immediately we're going to rename this notebook to something like Poisson, because We don't want our workspace to become untidy. I realised that last time we left our notebook unnamed, which is not terribly brilliant practice, but we'll keep it like that for now because I think there's a big housekeeping video to come. Because if you look in my old code, so if you look in this repository here, football-stats, there's actually a huge library just here which contains all kinds of lovely convenience functions for us to play with. This big bet tools library that I wrote is something you should dive into if you're really interested and kind of like break it apart and understand what's going on. It's got all sorts of things like get data functions which reach into footballdata.co.uk and do all of the stuff that we did in the previous few videos in terms of grabbing data and handling it and pulling it out nice. There's what we're going to look at today, which is this Poisson match outcome stuff, and there's lots in here that you could just have. It's all yours. Go get it. So the way that we're going to approach this is that we're going to start by looking at the raw equation, and then we're going to move on to something a little bit more advanced. And by moving on to something a little bit more advanced, we'll be able to do some fancier things. But I really want to start in that actual Poisson equation so that we understand what is happening. So the first thing that we're going to do is we're actually going to code up that equation. To do that, the first thing we will need is we need numpy as np. So we're going to import numpy as np. And then what we want to do is we want to write a function that we give lambda and k to, and then it returns to us the actual answer that we want. So we might write something like Poisson. I'm going to call it Poisson PMF, I think. And the reason that we're going to call it Poisson PMF is because other things use the name Poisson, and I don't want to get confused between them. And PMF is probability mass function. It's just a fancy word for that curve. Don't worry about it, doesn't matter. And that wants to take lambda, and also, oh no, I can't use the word lambda. That's a good catch by Python there. So lambda and just k. Because remember, in our equation that we are going to replicate, it lambda to the k with e to the minus lambda over k factorial is what we want. So we've got lambda, we've got k, and I want to return the probability, I think. That's what I want to return. So this is, if we, hang on, I'm going to stick this equation over here so that I can refer to it because we're going to write it out. So lambda to the k, so the probability is equal to lambda lmbda, still recording, good, to the k, we'll stick that in brackets like so, and that is multiplied by np.exp. So this bit here, this, come on. So this here is the exp function, e to the, so it's np.exp, np.exp minus lambda, mlbda, and that is all divided by np.factorial. One moment, I'm going to go off camera and check that it's np.factorial, not np.math.factorial, because I seem to remember that that's what it is. One moment. I was, in fact, barking up the wrong tree entirely. We need to import the math module. Import math, like that. And what you need here is not np.factorial, it is math.factorial. Math.factorial, k. That then should work. We can, in fact, test this. All right, there are online Poisson distribution calculators that we can compare our answers to. So just to make sure that we've got our equations right, we can go Poisson PMF. And then what this really means is that if we think there are going to be, let's say, one goal in a game, what's the probability of there being 3? And you can see that that equation is giving it out as 0.061. If we compare our work to this thing over here, then 0.061. So far, we're doing great. However, we can do a little better. So let's leverage SciPy at this point. So we're going to import SciPy. No, we're not. Apologies, reading my notes. From SciPy.stats, import Poisson. Like that. And what that allows us to do is basically contain this. So this function that we've brought in here is just this, but a little bit less messy. And where we're ultimately going is we want to be able to use the Poisson distribution to predict the probabilities of the outcome of a game. So let's start to do that. So let's define what function we might need. So what I want to do is calculate Poisson match outcomes. And I would like to take in a home goals expectation and an away goals expectation. And what I would like to return is home win prob, draw win prob, and the away win prob. That's what I would like to return, like ultimately. So I want to use the Poisson distribution so that I can give you a number of expected goals. Like say, I think that Man City are at home against Bournemouth and they're going to beat them 3-1. So we have a home goals expectation of 3 and an away goals expectation of 1. What does that actually mean for the probabilities that I'm interested in, and therefore what odds would I find it acceptable to bet on, is basically where we're going with this. So the first thing that we need to do is we're going to run through a large number of goals and basically calculate the probability for each of them given the expectation. Now that sounds like a load of nonsense, so I'm just going to explain it in code. So we first of all define an upper limit. What's the upper limit of goals that I want to think about? And I'm going to set that answer at 10. It's extremely unlikely that there are going to be that the home team or the away team is going to score 10 or more goals. So we're just going to ignore everything above that. One of the assumptions that we're starting to make, welcome to the world of maths. Then what I'm going to say is that the home probabilities are equal to, and I want a list of probabilities at that point. So what we're going to do here is we're going to create this list, which is that, so I'm going to put in a home goal expectation, say like 3. What I want to then do is get every probability out from 0 through to 9 for each of those goals. So like, what's the probability, if I think there are 3 goals, using the Poisson distribution, what's the probability of there being 0? What's the probability of there being 1, 2, 3, 4, etc.? And we're going to put those into a list. And we're going to use, oops, I obviously got very carried away mashing the keyboard, but what we're going to use is the Poisson thing from up here. So let me show you how this works very, very briefly. And it just to prove that it works kind of in the same way that we coded up earlier. Poisson.pmf of, say, 3 and 1. And the reason that I've picked 3 and 1 this way around, where we did 1 and 3 last time, is actually confusingly the way that this works is it's the opposite way round to the way that we coded up for ourselves. So it's actually this. So I'm going to swap these around now so that we can remember what's going on. So what this is saying, and this is the same answer that we got before, as you can tell, when I expect 1 goal, what is the probability of there being 3? Therefore, we're going to do a little bit of list expansion here. So what we're actually going to do is we're going to run through each of the goals from 0 to the max goals. And for those, we are going to get out the probability of that number of goals occurring given the home goals expectation. So the way that works is we go Poisson .pmf, and then it's I home goals expectation. Yeah, that's the one. For I in range 0 through to max goals plus 1. And what that will do is it runs through all of the possible goals from 0 up to 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and including 10 because we've done max goals plus 1 here. And for each of those, it puts into the list the probability of that number of goals occurring if our home goal expectation is whatever we pass in. So let's step into this and see how that is exactly working. So in order to step into this, first thing we're going to have to just do is make it not complain. And the way to do that is to do this, because if we step in and these don't exist, it'll be annoyed at us. So We're just going to define these as 0 for now. Obviously, we will change them in a moment, but we're just going to define them as 0 because what I want to do at this moment is print the home probabilities. Now, you should use a debugger to do this because it will stop you having to do this nonsense. And it's just a more elegant solution, but I can't be bothered right now, so we're not going to do that. Right, having read that in, what if we do calculate Poisson match outcomes for, should we say a 2-2 draw? Yeah, so if I think that the home team are going to score 2 and the away team are going to score 2, what happens? Now, it's printed out, the home probabilities, and the way that you read this is you read it for each of the goals. So at the moment I'm saying, I think that the home team's going to score 2. So what's the probability of them scoring 0? Well, it's 0.13. The probability of them scoring 1 is 0.27. The probability of them scoring 2 is 0.27. 3, 0.18, 4, 0.09, 5, yada, yada, yada. So with this, we can now repeat that process for the away team. So we can go, in fact, you know what? I'm just going to copy and paste. You can copy that, you can paste it here, and we can now say that the away probabilities are equal to the away goals expectation for I in this range here. Let's just do some cleaning. So what we now have is we have 2 arrays of the probabilities of goals being scored. And what we're really interested in is what are the probabilities then for the different results we could get. Now, the easiest one to visualize is the draw probability, because what we have to do is we have to take all of the probabilities where the home team score the same number as the away team and add them up. So let's do that. In order to do that then, what we are interested in is when one team scores a number of goals and the other team scores the same number of goals, we're going to take that level of probability and add it to all of the others. Now, you'll remember from like GCSE statistics that to get the conditional probability of 2 events, you multiply them together. So the probability of it being a 1-1 draw is the probability of the home team scoring 1 multiplied by the probability of the away team scoring 1. And what we want to do is do that in our like conceptual matrix for 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, yada, yada, yada. We're going to do that in some list comprehension. So the draw win prob is equal to the sum of the home probabilities, I, multiplied by the draw probabilities, sorry, it's not draw probabilities, it's away probabilities, my fault. Got draws on the mind. So we're going to multiply those together for I in range, max goals plus 1. So what this does is it multiplies together and it adds up everything for 0, 0, 1, 1, 2, 2, 3, 3. So we can get rid of this now, draw win prob, and we can run this. And what I'm interested in now is calculate Poisson match outcomes. And we were doing, I think, 2, 2. So if it's 2, 2, if I have an expected number of goals of 2 for each of the teams, what's the probability of there being a draw? It is an error because I've managed not to spell probabilities right again. I hate the word probabilities. Hang on. The problem here is that. Let's read that in. The probability of a draw is 0.207. Now let's deal with home and away. So we're kind of going to do the same thing, all right? But the comprehension is a little bit more complex because, so let's think about a home win for a second. What we want is we want to figure out for any given number of home goals, what is the probability that the away team scored fewer? So we want to multiply together the conditional events. So we want to figure out what's the sum of the probabilities. So let's say the home team scored 2. What's the sum of the probabilities where the away team score 1 or 0? So what we're going to take is those events, 2, 1, 2, 0, and we're going to add the probabilities of those up. But to get the probabilities of those events, 2, 1 and 2, 0, we have to multiply the probability of the home team scoring 2 with the away team scoring 1, and then that's 1 probability. And then we go, well, what's 2, the probability of 2 multiplied by the probability of 0, that's the other probability, and we add them up. Now we want to do that programmatically over every single possible scoreline. So to do that, we're going to do something that looks a lot like that draw code, but we will do it in a slightly more complicated way. Let's put it here. Home win prob is equal to, and again, we're going to take the sum. And what we're going to do now is we're going to take all the home probabilities I, multiplied by, and here what we're going to do is the sum of the away probabilities, because that is the same. The sum of the multiplication is the same as the multiplication of the sum, because multiplication is distributed. It's distributed. That's how it works. So what we can do here is sum away probabilities. Oh my goodness, I cannot spell this word. That cannot become the curse of this channel, is being unable to spell the word probabilities. But that's fine, okay? And everything up to I. So remember, if we've scored I, what is the sum of the probability? We will then want to be multiplied by the sum of all the probabilities of everything up to I. For, as you will be unsurprised to learn, for I in range 1, giving my cursor back, 1 to max goals plus 1. The reason that we start at 1 and not 0 is because you can't win a game if you've only scored 0 goals. So we need to start at 1. We can then replicate this for the away win prob. So let's do that. Away win prob is the sum of the away probabilities I multiplied by the sum of the home probabilities up to I for I in range 1 to max goals plus 1. Right. Tiny bit of housekeeping, we can get rid of those. So now, if we have the lively expectation that both teams are going to score 2, what are the probabilities of the outcome? I cannot spell. This is really going to become the meme of this channel, isn't it? For goodness sake. Right. Where is it? Home win prob. I just can't spell the word probabilities. Good gravy. There. Right. We all good? I think we're all good. No. I'm going to jump cut to where this is fixed. It's fixed. Right. If we think it's going to be 2-2, what's the actual outcome? Right. This tells us that the probability of a home win is 0.396. The probability of a draw is actually 0.20. And the probability of an away win is 0.396. And this is nicely symmetrical. Also nicely also nicely illustrates a problem with this distribution, and potentially one of the reasons that we saw differences before, way back at the early part of the video, is that this takes no account of home advantage whatsoever. Home advantage is clearly a thing. Okay, we can statistically prove that home advantage is a thing in the English League. Maybe we'll do that sometime. But this doesn't take that into account. So when we expect a 2-2 draw, it's actually predicting that the home team and the away team have an equal chance of winning. If you thought there was going to be a 2-2 draw in actual fact, you might want to modify the home team's probability because, well, home teams are more likely to win at home given a certain expectation. Anyway, that is enough of this for now. I've illustrated my point and we're going to just hold it here for this week because you can now go and use this function. And I would encourage you to. If you think that a certain scoreline is the most probable one, then go ahead and use this function to create your own odds book. You can start to draw a line. One of the things that we're going to work on over the next while is how do you come up with that expectation? What is a good method of doing that? Anyway, my name has been Gonzo. Like, subscribe, all that garbage. I'm getting better at the analytics stuff. There may even be end cards in this, but there probably won't. So just go and watch my videos.